Hello everyone. In this video we are going to discuss some basic topology and some important definitions related to the metric space. So some important definitions. Number 1, a neighborhood. Neighborhood of a point, and it is denoted by, in short, we will write NBH. Let X be a metric space so a neighborhood of a point P is a set denoted by NRP consisting of all points Q such that dpq, the distance between P and Q, is less than R, and the number R is called the radius of this open set, this set NRP, whose center is at P. This is called the neighborhood of a point P. Suppose we have a metric space X. P be any point in the metric space, then the neighborhood of P is denoted by NRP, and it is the collection of all those points of X such that the distance between P and Q is less than R. So this set is called the neighborhood of P. Now the next definition is very important, and the definition is of limit point. A point P is a limit point of the set E if every neighborhood of P contains a point Q which is not equal to P, that is different from P, such that Q is in E, then the point P is called the limit point of E. Now the third definition, closed set. Let E is closed set if every limit point of E is a point of E. That means a set is called closed if it contains all its limit point. Now the third definition is open set. E is called open if every point of E is an interior point. If every point of E is an interior point of E. And what is the interior point? Let X belongs to E, then X is called interior point if there exists an open interval I such that X is contained in I is contained in E. Then X is called the interior point of X, point of E. Now let's see some definition, some theorems. Theorem number 1. Every neighborhood is an open set. Now the proof. Consider a neighborhood, say E. E is the neighborhood of a point P. Let Q be any point of E, then there is a positive real number H such that dpq, the distance between P and Q, is equal to R minus H. And for all points S such that dqs is less than H, so we have dps less than or equal to d of pq plus d of qs, which is less than R minus H plus H. This is equal to R. This implies d of ps is less than R. Hence we can say that S belongs to E. Thus Q is an interior point of E. Since we know that a set is called open if every point of that set is an interior point, so we have a neighborhood denoted by E. If we take a point Q in the set E and we have proved this Q is an interior point of E, this implies we can say that E is open. This implies E is an open set. Now the second theorem, theorem number 2. And the statement is, if P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. And the proof of the theorem: suppose there is a neighborhood N of P which contains only finite number of points of E. Let the numbers are Q1, Q2 up to Qn be those points of N intersection E which are distinct from P, and if we take R is equal to the minimum of P and Qm, where m lies between 1 to n, so we can see that it is very clear R is always positive. Suppose this is a set E and we have a point P, and this is the neighborhood NRP, and this neighborhood contains finite number of points, and the points are, suppose, Q1, Q2 and so on Qn, and we take the minimum of P and Q. Suppose this point is minimum, nearest point is this, suppose nearest point is this, and no point is nearer to P in this neighborhood, so we have this distance is R according to our assumption, and so we get a neighborhood of a point P such that this neighborhood contains no point Q of E which is different from P, that is, the neighborhood NRP contains no point Q of E such that Q is not equal to P. This implies P is not a limit point of E. This contradicts our fact that if E is a limit point, if P is a limit point of a set E, but we have proved P is not a limit point if we assume the points are finite. This implies this contradiction establishes the theorem. So the points must be infinite. Now we have a assignment. Prove this corollary: a finite point set has no limit point. Now the next theorem, and call it theorem number 3. Let the set of E alpha be either finite or infinite. Collection of sets E alpha, then the complement of union of E alpha is equal to the intersection of the complement of E alpha. Now the proof: let, for the sake of convenience in writing, we call it A, the left hand side part, it is A, and B is the right hand side. We call it B, and this left hand side denoted by A. If X belongs to A, this implies X does not belongs to union of E alpha, because X belongs to A means X belongs to the union of the complement of E alpha. If the number is in the complement of this set, then it does not contained by this set. Hence X does not belongs to E alpha. If it is not in the union of E alpha, so it will not contained by any E alpha for any alpha. This implies if it is not in E alpha, it must be in complement of this set for every alpha. This implies X is in the intersection of E alpha. This implies X belongs to B. It is nothing but B. This implies A is contained in B. We call it this equation 1. Now conversely, if X belongs to B, that is X belongs to the intersection of E alpha, complement of E alpha. This implies if it is the intersection of this implies X is in E alpha complement of E alpha for every alpha. This implies X is not contained in E alpha. If X is in the complement of this set, then it will absent in this set for any alpha. Hence we can write, if it is not in E alpha, so it is not in the union of E alpha. This implies X is contained in the intersection of this union. This implies X is in A, it is nothing but A according to our assumption. This is A. So X is in B is contained in A. This implies B is contained in A. We call it 2. So by 1 and 2, by 1 and 2, it follows that A is equal to B. Hence proved. Next theorem, and theorem number 4. A set E is open if and only if its complement is closed. Proof. Suppose complement of E is closed. Let X belongs to the set E. This implies X is not in the complement of E. This implies X is not a limit point of E. Since we assumed E complement of E is closed, that means it contains all its limit point. No limit point exists outside of this set. If X belongs to E, this implies X does not belongs to the complement of E. So X cannot be the limit point of the complement of B because it is closed. Hence there exists a neighborhood N of X such that complement of E intersection N is equal to phi. That is, N is contained in E. This implies X is a interior point of E because we have a neighborhood of X which is contained in E. This implies E is open. Now conversely, let E is open and let X be a limit point of complement of E. Then every neighborhood of X contains a point of the complement of E because X is a neighborhood. of complement of E, then every neighborhood contains actually infinite many points of the complement of E. This implies X is not an interior point of E. Since E is open, this implies X does not belongs to E, because if X is not an interior point of E and E is open, then X does not belongs to E. This implies X belongs to the complement of E. This implies complement of C is closed, because we assume that X is a limit point of the complement of E and it contained in the complement of E. That means this set is closed, because according to the definition of the closed set, it contains all its limit point, hence proved. Now move to the next theorem, and theorem number 5. It has actually 4 parts. Part 1: for any collection of open sets G alpha, union of G alpha is open. Part B: for any collection F alpha of closed sets, the intersection of F alpha is closed. Part C: for any finite collection G1 up to Gn of open sets, intersection I from 1 to n Gi is open. In the last part, part D: for any finite collection F1 F2 up to Fn of closed set, union of Fi is closed, I from 1 to n, and we prove it one by one. The proof of the part A: let G is equal to union of G alpha, the union of the open sets. If X belongs to G, then X belongs to G alpha, because G is nothing but the union of G alphas. If X is in G, so X is in every open set. For some open for some alpha, it must contain by any of G alpha. Therefore, X is an interior point of G alpha. This implies X is also interior point of G. Hence we can say that G is open. Now the part B, proof of the second part B, and the part B is the intersection of closed set is closed for any collection. Proof of B. We know that since C alpha is closed, this implies by the theorem number 4 we can say that the complement of F alpha is open. This implies the union of open set is open. And by the theorem number 3 we know that intersection of F alpha, the complement, is equal to the union of the complement of F alpha. So if it is open, this implies it is open. This implies union of alpha, complement of the intersection of F alpha is open. If this is open, that means F of the intersection of F alpha is closed. So this proves B. Now we are going to prove the C part. For any finite collection of open set, then the intersection is open. Let H is the intersection of GI's, i's from 1 to n, and let for any x belongs to H, there exist neighborhoods Ni of x with radii Ri such that Ni is contained in Gi. Since all the Gi's are open, so every point of all Gi's must be the interior point. That means there must exist an neighborhood which contains x is contained in G, the open set G, for I is equal to 1 to up to n. That means n1 is the neighborhood of in G1, n2 is the neighborhood in G2, and so on. Now take R is equal to the minimum of R1, R2 up to Rn, and let n be the neighborhood of x of radius R, then n belongs to Gi for I is equal to 1, 2 up to n. This implies n belongs to H. Hence we can say that H is open. Now the proof of the D part is very easy. By taking complement D follows from C. If we take the complement of D, we get the Dth part. So thank you for watching this video, and in the next video we will discuss some more basic definitions related to the metric space. Thank you.